Okay, good morning. Please answer, is the screen visible here?
Yes, sir.
Okay, last class we have seen the single phase current source inverter, and now the single phase current source inverter, how it works the same way the three phase also works, except the circuit diagram is different. We have three phases here instead of one phase. Okay, that's the only difference you will find out. There is no other difference. I'll just draw the circuit diagram here. So this is the three phase current source inverter. It's very similar to the single phase current source inverter. Okay, so now like in case of your three phase voltage source inverter, here also you will get a waveform for the single phase current source inverter. You have, this is the shape which is very same. This is very same as the previous case. Okay, so then it is a non-sinusoidal one. So as it is a non-sinusoidal one, this is IA. You can take any one phase. So this height you can take it as ID. This ID is this one. This is ID. Okay, that is ID. So this is a non-sinusoidal one. So then it will resolve into uh, sinusoidal components using the Fourier series. So there also same thing, that at the end what we will find out is that is proportional to ID. So the current IA, whatever the expression you got, at the end I can write this signal is proportional to ID. So now you see here these three terminals will be connected to the induction motor. These three terminals will be connected to the induction motor. So the current in the induction motor is proportional to ID, which ID this ID here. So the current source value. So by varying the current, we have seen already in the last class itself, we have seen that the stator current, if you vary, then the speed and torque of your induction motor also vary. This we have seen. So likewise, we will use this three-phase current source inverter to control the induction motor. Okay, and then yeah, another topic: how do you operate this current source inverter in multiple operation? We have seen in case of voltage source inverter how to operate in multiple quadrants. So to operate in multiple quadrants, we have last class what we have seen is that we will make yeah, this is a recall that this star minus t plus omega minus omega. So simple thing that this is motoring, yeah, forward motoring. This is forward braking. This is reverse motoring and reverse braking. So I hope you know what to do for braking. For braking condition, you reduce the frequency of the stator. So if you reduce the frequency of the stator, if you reduce the frequency of the stator, then obviously it becomes negative. It becomes negative. Okay, then the power will become negative. So it goes into the braking condition. Okay. Whereas when you want to make a omega negative, what you do is that you change the phase sequence. You change the means you change the connections. See how three terminals are there. We have three terminals there, so we have three phases. So rather than we make it as RTA. When you want phase sequence, we find out is the phase sequence. Okay, the motor speed will get reduced. So you will get minus omega. So because an operate very similar to your very similar to your previous cases. Okay. So regenerative braking. So this is how you multi-point operator. So now what about the regenerative braking? Regenerative braking is there. So in the regenerative braking method we have seen obtaining collective power. So to collective power we have seen a three block diagram. You 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 just connect them you just collect the power back. So you operate in this forward braking method or sometimes in the reverse braking method also, you can connect the power. See, regenerative braking method, whichever I explained in the case of the old method, same procedure you will follow here also. Here also you follow the same procedure, you get that. Except here it is a current source, whereas the previous case it is the voltage. There is no other difference in case of the multi-important operation and regenerative braking operation. No other difference. Okay, then we will go now closed loop control of. I will say now slip controlled, closed loop slip controlled current source inverter, current source inverter drive, CSI drive with regenerative braking. So this case I will draw the black diagram and I will explain. Okay. So we'll start from this side. So control 55 with the AC supply. Then we have inverter. We have the firing circuit here. Then we have current controller. Now you can start here. Okay, now you see, yeah, this is the block diagram. So now see this block diagram. So now you see here, we'll search what is there here. So what is there here? See, this is the induction motor. Okay, this is the induction motor. So the supply to the induction motor you are getting from the current source inverter. Now you know what is the so in the current source inverter how you are getting the supply, just recall. The AC supply is there, then you have rectifier, then you have a large value of inductor. A large value is there, then this ID will remain constant. Then it goes to the inverter. Then after that, this DC will be converted into AC using this current source inverter. So you got this. Then what are the things you require for these things we will see now. First of all, these inverters are there. So these inverters, so you need the firing pulse to the inverter. Okay, you need the firing pulse to the inverter. So you need the firing pulse to the inverter. So how you are getting the firing pulse here is that series you are getting the firing pulse from this part. Okay. Okay, we will see what is that part later also. Then this is a control rectifier. So control rectifier in the sense the rectifier having thyristors. It's not a bridge rectifier. It's a thyristor rectifier. Then for the thyristor rectifier you require the firing circuit. It's important. Using the firing circuit is there. So now if you see the feedback path, so this is the power circuit. The circuit which is there, AC supply, control rectifier, then the inverter, then the induction mode. This entire thing you can call it as power circuit. Remaining all things you can call it as control circuit or feedback path. Okay. Okay. Now you see, we will see the feedback part. What is happening in the feedback part? What is happening in the feedback part is that first you are sensing. See here, you are sensing the speed here using the speed sensor. So that speed is this one. So this is the rotor speed. You can call it as rotor speed. This is the rotor speed. Okay, now you see there is a summing point here. So at this summing point, what exactly you are doing? You are adding omega SL with omega M. Then you are generating omega MS. Now this is the rotor speed. This is the rotor speed. So I will take it as NR, rotor speed. Now what is this omega SL is that? Omega SL is nothing but it is the slip speed. You call it as slip speed. Okay. Slip speed. So slip speed in the sense I will tell you S into NS. S into NS you can call it as slip speed. Now what is this omega ms is that it is synchronous speed NS. We'll check now whether it is correct or not. See here this is rotor speed. So there is a summing point. So you are adding rotor speed with the slip speed. So when you are adding rotor speed with the slip speed, what is the answer you will get here? Please see, recall. SNS is the slip speed. So you add SNS with NR. You add SNS with, so what is SNS here? It is nothing but omega SL. Here in the picture I'm just showing you here, it is omega SL. Whereas this is omega M. When you add SNS plus NR, what is the answer you will get? What is the answer you will get? Recall the slip definition. Slip is equal to NS minus NR by NS. So you do that NS minus NR by NS, that is S, into you multiply with NS plus NR. What is the answer you will get here? NS NS will get cancelled. NS minus NR plus NR. These two will get cancelled. So the answer is NS. So when you add omega SL with omega M, you are getting synchronous speed. Yes. This synchronous speed signal is going to the inverter. So what this signal tells here is that, see, from the synchronous speed, because synchronous speed NS is equal to, I hope you know, 120 F by P. Synchronous speed. So you are giving the information of synchronous speed in the sense you are giving the information of frequency. Because you see, for the inverter should know what should be the frequency of the induction. What is the rated frequency of the induction motor? So the rated frequency is this here. So that F you are getting from information of NS. How you are getting NS? You are getting NS by adding slip speed with the rotor speed. How you got the rotor speed? You are getting the rotor speed. You are getting the rotor speed from the sensing of the actual rotor of the induction motor. Whereas how you are getting the slip speed here? That's the question. So how you are getting the slip speed here is that you are getting the slip speed from the flux control box. So now recall the flux control box. Recall the flux control box. So what is the relationship between flux control and the slip speed? You must understand this thing. What is the relationship between this? So here you see carefully that your slip speed is nothing but SNS. SNS, okay. So SNS, what you have here, SNS is that it is SNS. It is the, so it has some frequency. SNS has frequency. What is the frequency SNS? It has SNS. It has the frequency F, or we can say S into F, because NS is proportional to F. So I will add here SNS is proportional to SF. So now why do you require the flux control here is that, so this flux control will control the frequency. Why it is controlling the frequency? You recall the last class frequency control, stator frequency control. Okay, in the stator frequency control, what did you learn there? You learned one thing, that one graph. If you recall that graph, I will recall the graph here. This is the frequency. This is the stator voltage. So there is a relationship between stator voltage and the frequency. What is that one? Is that till you reach the rated voltage, or rated frequency, till you reach the rated frequency, the relationship between stator voltage and F is direct relationship, Vs proportional to F. Okay. Whereas beyond the rated frequency, even though you increase the frequency, you maintain the voltage constant. Okay. So this is the frequency control. Why this? How this frequency control is related to flux is that, you know very well why we are doing this. That when the frequency is less, we have seen ourselves. What we have seen ourselves when the frequency is less, we have seen this thing that flux is proportional to V by F. I will just rewrite this picture once again. When the frequency is less, your flux is more. So when the flux is more, then the core enters into saturation. So you don't want this. So you need to maintain the flux constant. So to maintain the flux constant, what you do? Whenever the frequency is reduced, you reduce the voltage also. So till this rated frequency, if you reduce frequency, you reduce the voltage also. If you increase the frequency, you increase the voltage also. So you maintain the flux constant. So that's the flux control box here. So based upon that flux control, okay, you will get this command. What is the slip speed? S into ns. Because the flux control is related to frequency, and your slip speed SNS is also related to frequency. So combinedly, the flux control box will generate this command. Which command it generates? The slip speed it generates. Okay, and also it generates here this, and also it is related to the current. Which current here it is related to? Stator current. You can call it as why stator current. See, this is the reference stator current. This is the actual stator current ID. You are sensing ID here from this. See this one. You are sensing ID here, and that ID is compared with the reference ID. That is reference stator current. So how you are generating the reference stator current? You are generating the reference stator current once again on the flux control box. So how you are getting the from the flux control box is that I told you already. This flux control box, that is phi, is related to frequency. Now last class we have drawn a graph, another graph we have drawn. I will just recall the graph here. We just recall that. It is the stator current. And it is the rotor frequency. So there is a relationship between rotor. Yes, is the rotor frequency. You must recall this thing, the induction motor operation. SF is the rotor frequency. So SF is the rotor frequency. So rotor frequency is related to the stator current. So whereas the rotor frequency SF is related to the flux control, because it has F. So F is related to flux. So combinedly we can say this flux control has two things. So flux control box, it is related to flux, and also it is related to stator current. It is related to frequency, and also it is related to stator current. So this flux control box is also generating the stator current. So that is ID star. So reference stator current. So whichever is required, what is the required stator current? It should be. So that will come here. So the ID which you generate here, it may not be equal to the reference value. How you are generating the reference value? You generate the reference value based on this graph. You generate. So how do you decide the rotor frequency here? The rotor frequency is decided by the flux. So flux is the center for both your slip speed and also for the stator current. By using these graphs, I hope you can understand, and these equations that flux is the central point here for the slip speed and also for the stator current. So they will generate the reference values. So here the reference current and here the slip speed. Okay. Now going to this side, that is the reference stator current. Then this reference stator current will be compared with the actual stator current. So you may have a current sensor here. Here you may have a current sensor, and you see here, this is the ID that is going to the current source inverter. So that ID will be sensed here. If there is an error, then the current controller will act based upon the command of the current controller. Firing circuit will give the firing pulses to the control rectifier. So whenever there is error in the stator current, that is ID or the DC current to the inverter. Whenever there is error in this current, that because of that error, you have the controller, and based upon the control current, based upon the error, the firing circuit will give the triggering pulses to the control rectifier. So this makes a closed loop. So now what you must understand here is that, one more thing you will understand here is that, I said that the slip speed is there. Yes is there. So how come this is here? So you are getting the S from this speed, how you are getting it? You see here, now the same speed you are getting here. This is your actual speed of the rotor, and that actual speed will be compared with the reference speed, because you will set a reference speed always, the rotor speed. Then if there is an error, then speed control will act. Then after the speed controller, then you have the slip regulator. So slip regulator will regulate the slip between 0 to 1. Okay, if it is motoring condition. If it is regenerative braking, then it will be controlled. It will be controlled what negative value, that is less than 0. Here, what is the purpose of slip regulator here is that to control the slip between 0 to 1 for motoring condition. Whereas for braking condition, we have seen this thing. For braking condition, slip becomes negative, so it becomes less than 0. So two operations are there in this. So one is motoring, the other is regenerative braking. So regenerative braking in the sense, braking in the sense itself, it is slip is negative. So the purpose of slip regulator here is that either it will be from 0 to 1 or it will be less than 0. So once again, I will repeat this entire picture. What is there? You have the induction motor here. Then the induction motor supply you are getting from this current source inverter. The DC supply to the current source inverter you are getting from this controlled rectifier, and you have the inductor. Okay. Then how you are getting the firing pulses to your controlled rectifier is based upon the current command. So the actual current and the current command both will be compared, and then this makes a closed path. So you will get the controller and the firing circuit. So you will get the pulses. So the firing pulses on this control rectifier, they depends on the error in the DC current, that is ID and ID star. How you are generating ID star? You are generating ID star from the flux control. So from the flux control, you see the flux. The flux equation is related to frequency. Okay, and the frequency is related here. You check yourself this graph, second graph. In the second graph, in the second graph, frequency has a relationship with the IS, that is the stator current, whereas the frequency is related to flux here. So indirectly I can say flux has a relationship with the stator current. So based upon that relationship, this flux control box will generate a current command here. Then it also generates slip speed. Okay, what is slip speed here? S into ns, that is the slip speed. So it generates the slip speed also. Now this slip speed, when you add with the rotor speed, that is slip speed plus nr, will give ns as per the slip definition. So that ns is here. So this ns has a relationship with the frequency. Which frequency? The rated frequency of your induction motor. So based upon this ns value, f will be decided, and based upon the value of f, the inverter will generate a supply which is having a frequency equal to this f. Okay. And coming to this last feedback path, what is this last feedback path? Is that it is a speed control path. So the actual speed you take here, then you compare with the reference speed. Then if there is an error, then it will go to the speed control box. Then it will go to the slip regulator. What is the purpose of slip regulator here is that if it is motoring condition, you make it from 0 to 1. If it is a braking condition, you make it less than 0. This is the closed loop controller current source inverter, okay, of this induction motor. Then okay, then we go. Now we'll go to another topic, that is comparison of CSI and VSI. That is voltage source inverter. That three comparison points are there. Important points are there, so we will discuss those points. First thing is that CSI is more reliable. On drug bill. What is the reason? First of all, I will tell you why you are calling it as more reliable drug. You see yourself here. Okay, so you see here this is an inverter. Here you have DC supply. This is voltage source inverter. Whereas if you have current source, we call it as current source inverter. That is the only difference. And remaining all are same. Okay. Now you see here. So why we are calling as more reliable? Because I will take one case. Accidentally, say for example, these two switches are on at the same time, or these two switches are on at the same time. Accidentally, it may happen. So in that case, what will happen? If you have a voltage source, that is V. If you have voltage source V, and when it is short circuit, then the resistance value is very less. When the resistance value is very less, then what is the current flows in this? The I is equal V by R. R is very small. Then what is I value? I will be very large. So when you have the voltage source inverter, say accidentally these two switches got short circuited. these two switches are turned on at the same time. It means something like you did not provide the dead time or some other reasons. Assume that both the switches are turned on, okay, simultaneously. When they turn on simultaneously, it acts as a short circuit. When it acts as a short circuit, voltage source short circuit. What is the current flows in that? I is equal to V by short circuit resistance is very small. Then what is the value of I? I will be very large, and that large current will damage the switches. Coming to the current source inverter has a value of I, and you know current source value is constant. Similarly, voltage source, for example, I said 10 volts, then 10 volts is constant, whatever you connect here. Whatever you connect here, 10 volts is constant. Similarly, current source in the sense, for example, 5 ampere current source. Then whatever may be the load here, this 5 ampere remains constant. So now you take in this case, when you have the current source, then even though there is a short circuit, what is the current flows in this short circuit? Only 5 ampere, not more than 5 ampere, because its value is constant. That's called current source. Whereas voltage source is its value is constant. That is 10 volts. So whether it is short circuit or open circuit, its voltage is 10 volts only. So then I value is how much? I is equal to 10 by some resistance value. How much it is? 0.0001 something. Then you will get around 1000 ampere. So 1000 ampere current will flow through this short circuit. So these switches will get damaged when you have the voltage source. But when you have the current source, something like this, there is a current source and there is a short circuit across this. For example, this is 5 ampere. Then what is the current in this short circuit? 5 ampere only. This 5 ampere will not damage the switches here. But when you have the voltage source, 10 volts, and you short it, then what is the current flowing in this case now? I is equal to 10 by R value, very small value R, that is a short circuit. So I value is very large. So large amount, some 1000 ampere something. So this will damage the switches. So that's the reason that current source inverter is more reliable and rugged compared with the voltage source inverter in this point of view. Okay. Now second difference is that, see, dynamic braking is not possible. In current source inverter. That is the second point. You recall the dynamic braking what we have done in case of voltage source inverter. You have a switch here, then you have a resistor here, then you have another BJT here. Okay. Then this side you have a capacitor. Okay. Then you have remaining things are there. Okay. So now what we have seen here, this is the motor, say for example. What we have seen there is that, for example, during dynamic braking, what you do now, you recall that you turn on the switch, so the current will flow through this resistor. So when the energy is flowing through this resistor, the energy will be dissipated through this. Okay, in case of the voltage source inverter. But coming to the case of the current source inverter, okay, so the current value is constant. So when the current value is constant, this I value is there. Okay, when I value is constant, here, what do you find out here when I value is constant? Even though you turn on the switch here, the resistor will be there. The constant current will flow forever. Why it flow forever? Because the current source is constant. So it will flow forever. So the I square R is always dissipated. I square R is always dissipated in this. So whereas in case of the voltage source inverter, this I value gets decreased. When I value gets decreased, the power dissipation slowly gets decreased and it will end at one point. Whereas in case of I, practically it is not possible because I remains constant every time. So if I remains constant, R value is also constant, then I square R is always constant. So the power dissipation is always constant if you have the current source inverter in this case. Okay, then the power will be dissipated and okay all the time. Then that so the entire current source, its energy goes through this resistor. So it's a waste of power. So practically we will not use this dynamic braking, and it is not possible in case of the current source inverter. That is the second point. Now third point is that what is the difference between the current source and voltage source inverter? In the current source inverter, you need a large inductor, very large value. If it is large value, then only the current here is constant. Otherwise, the current is not constant here. Okay, so large value of inductance required in current source inverter. Whereas in case of your voltage source inverter, you don't require that much large value of inductor. Okay, a small value of inductance is enough. And because of this large inductance, there is another thing is also there. So this large inductance may affect the dynamic response or dynamic performance of the system. Because I hope you know this thing that any system called to be dynamic when the system has energy storage element. Now you are having a very large value of inductor. So this large inductor will affect the dynamic performance of your okay, dynamic performance of your system. That is the third difference. Okay, and fourth difference is that your voltage source inverter is just sees your voltage source inverter is cheaper. I will say this thing. Why it is cheaper? Because you don't have this L value. L value, if it is large, then its cost is more. L value if it is large, its cost is more. Okay. And another, so these are the four main differences. Other than this, you have some more differences also. What are the other differences that? One difference is that you will use the current source inverter. You will use the current source inverter for uh, for low speed range. You will use for low speed range. Okay, why you will use for low speed range is that simple answer that see here. Why you don't go for the high speed range? What will happen? So if the speed is low, see here if the speed is low. If the speed is low, then you know very well the frequency is low. It has a relationship. Speed and frequency has a relationship. So at lower speeds, obviously the frequency is also low. This is how you control the current source inverter. So at low frequencies, what is the advantage at low frequencies is that you can have flux constant. You can have flux constant because at lower frequencies to maintain the flux constant, you reduce the voltage also. So phi proportional to V by N. So this is better in case of the current source inverter. If you reduce the frequency, your voltage also you can reduce, so you can maintain the flux constant. So making the flux constant in the sense, always remember the performance is very accurate whenever you make the flux constant. Beyond if F is large value, we have seen you maintain the voltage constant. So V is constant, but F is higher. Then what is the flux value? Flux value will reduce. Thus flux proportional to V by F. F is higher, whereas you maintain voltage constant, then flux becomes weak. So weak flux is there. So weak flux is there. The operation is poor. Okay. So in case of the voltage source inverter, you maintain the voltage constant. Okay. Whereas here you maintain the current constant. So you see here yourself. Okay. So